Okay, welcome back. The third point is the reduction in the voltage drop at a high voltage transmission means if you opt the high voltage transmission, so the voltage drop will be reduced, and that is what we are in need, that we should have the low voltage drop. So how the voltage drop is reduced? As we know that V is equal to IR, it can be noticed from the above expression that voltage drop in the transmission system is directly proportional to the amount of current. The greater the current, the greater will be the voltage. Higher the amount of higher will be the voltage drop in the transmission line. Okay, and vice versa. When the voltage is increased for the transmission by step-up transformer, the current in the transmission is reduced. So therefore, the voltage drop due to smaller amount of current will also be reduced. Thus, voltage regulation of the transmission system will be improved. Okay. So, fourth point is losses will be reduced at the high voltage transmission. The losses, the expression for the losses in the form of heat dissipation is P is equal to I square R. So, it means that power loss is directly proportional to the square of the current flowing in the transmission system. Mean the lesser the current, lesser will be the power loss in the transmission system, and vice versa. Therefore, if we increase the voltage of transmission system by step-up transformer, the current will be reduced, resulting in lesser power loss in the transmission system. Okay, power loss is equal to I square R. So as we know that P is equal to VI, I is equal to P over V. So replacing I by P by V, so we will get P square R over V square. So it means power loss is inversely proportional to V square. So if we have a high voltage, the power losses will be reduced. Fifth point is enhancement in transmission efficiency at high voltage. So as we know that input power is equal to output power plus losses. Input power is equal to P plus losses. Uh, Consider output power is equal to P. Okay. So the input power is equal to P per P plus we have calculated the losses in the previous slides. So P square rho L over A V square cos square phi. Putting the values of losses from the previous slide, so input power will be equal to P, which is the output power, plus this whole variables. Okay, so the current density, the current flowing through a unit area, that is represented by the J. So from this we have A is equal to I over J. Okay, so input power is equal to P plus this, replacing the value of A over here. So we will have J over I. Okay, now replacing the value of I from the previous uh, slides. So this is the value of I. Okay, so few of the variables will be cancelled out with from the numerator with the denominator. So we will get P plus this. Okay, now uh, this is the input power. Okay, so now the transmission efficiency is P out over P in. So we have P out is equal to P, and P input is this whole, okay, equation. So by replacing this over here, we will get P into the variables inside that bracket. So the P of numerator will be cancelled out with P. So we will have this. only. Okay, so this is in denominator, and when this variables are shifted to the numerator, so we'll have the minus power for this bracket. Okay, now using the binomial theorem expansion for the negative exponent, as we have studied in the junior classes, 1 plus x whole power minus 1 is equal to 1 minus nx plus this is okay. As we know that for the negative power, the higher terms are will be ignored because it has very low impact on the whole calculation. So this whole higher variables will be ignored. So same is the case over here. We have 1 plus this power minus 1. Okay, now 1 minus nx, so 1 minus n is we have 1. Okay, the n is equal to 1 in our case. So n is equal to 1, and now x, this whole variables of inside the bracket are x, so these are actually the x. Okay, so we will have 1 minus under root 3 rho lj over v cos phi, approximately, because the higher terms are ignored, so we have approximate. Okay, now uh, how the efficiency is enhanced by the high voltage. So for this purpose, we need to take some a real-time example so that it is more clear to you people. So let consider the rest of the variables as constant. So under 3 is already constant. So rho l j cos phi, these variables need to be constant in order to more clearly understand the efficiency enhancement with the high voltage. So for let's suppose we are taking the low voltage, V is equal to 5 volt. Okay, now replacing this 5 over here, so we will get 1 over 5. 1 over 5 is equal to 0 0.2. Okay, and 1 minus 0 0.2 is 0 0.8, and for the percentage of the efficiency, uh, multiply by 100, 80%. So now increase the voltage from 5 to 20 volt. So this is actually the case of high voltage. So what would happen with the high voltage? So by putting this value 20 over here, we will get 1 over 20 is equal to 0.05. Now 1 minus 0.05 is equal to 0.95, and multiplying it with 0.95, we will get 95%. Now, so the efficiency has been enhanced, and this is now quite clear from this real-time example that for the 5 volt we have the efficiency of 80%, and now for the when the voltage is increased, the similarly the efficiency, the transmission efficiency has also been enhanced by increasing this voltage. So therefore we have opt the high voltage for the transmission system. Okay, but it doesn't mean that by opting the high voltage for the transmission, uh, we have advantages over advantages, and we have no disadvantages in contrast. No, but on the other hand, we have to handle some of the disadvantages by opting the high voltage, and a few of these advantages are the corona losses. Okay, uh, this is not the corona virus, but the corona losses, and the electrical engineers are familiar with these losses. So we will discuss these corona losses in detail. We have an entire chapter for the corona losses. Um, after the after the midterm, that is in the final term course, yeah, we will study the corona losses, and we will study that how high would the high voltage have the corona losses and how to deal with these losses. Okay. And secondly, we have the problem of insulator, because the insulation level is increased with increasing the high voltage of the transmission line. As you may observe that for the 500 kV transmission, the insulation level is high, and for the 220 kV, and as we are reducing the voltage for the transmission and distribution lines, the insulation level is also reduced. Okay. Okay, and we will discuss the dielectric material in detail, but this is the brief definition of what is insulating materials. Insulating materials are also termed as the dielectrics. The difference in the name between dielectric and insulator lies in the application to which these materials are put. When these materials are used to prevent the flow of electricity through them, on the application of potential difference, then they are called the insulators or the passive dielectrics. On the other hand, if they are used for the charge storage, then they are called dielectrics or the active dielectrics. Okay. We have three major categories for the dielectrics: solid dielectrics, the liquid, and the gaseous dielectrics, and all of these have uh, their applications in different scenarios of the power system. Okay. These are the examples of solid dielectrics. They are mostly made up of ceramics or the glass. Okay. Or some are made with the composite material, means the mixture of the materials. And these are the example of the liquid dielectric, and we have taken the application of circuit breaker over the here. These are the contacts of circuit breakers. And these are the SF6, means the gaseous dielectric. Air is also a good dielectric, gaseous dielectric. Okay. And as we have observed that transmission lines are separated from each other, so actually by separating these, it means we have installed the gaseous dielectric between these two transmission lines. So, and in power system terminology, we call it clearance. Okay. The clearance between the transmission lines and clearance from the earth. Okay. uh, you know that the solid dielectric have the high dielectric strength. Okay. So what is dielectric strength, we will discuss it in detail in the next slide, but in the next lecture, sorry. Okay. So now for the briefly, dielectric strength is actually the strength by which any insulator or the dielectric can withstand the voltage. Okay. So how much voltage it can withstand? If we apply 10 megavolt of the voltage across a solid dielectric, for example, this is a solid dielectric, and these are apart by 1 centimeter distance, and 10 volt 10 megavolt, sorry, 10 megavolt of huge amount of voltage is applied, and these two are separated by a 1 centimeter distance. This is actually solid dielectric. So after the 10 megavolt, it will be a breakdown will be occurred for this dielectric. So it means uh, this is a very good insulator, very good dielectric, that it can withstand 1 centimeter of the gap. In the 1 centimeter of the gap, it can withstand 10 megavolt of the voltage in they are blocking this amount of voltage to pass. Okay. And then the second to the solid is the liquid, and they are the dielectric strength of the liquid are in the order of 1 megavolt per centimeter next to the solid. Okay. And mm, the lower dielectric strength are the gaseous as compared to the solid and the liquid, and they are in the order of 50 to 100 kilovolt. Okay, few examples of this is SF6 and air, carbon dioxide, nitrogen, etc. Okay. Okay, these are actually the curriculum, the chapters which we have to cover throughout this subject. And the next chapter will be electric field intensity, then the breakdown of the dielectrics. Uh, we will discuss the breakdown of the dielectric for the liquids in a separate chapter, and we have the separate chapter for the and the breakdown of solid dielectric and for the gaseous dielectric. Okay, we will discuss all of mm, the breakdown processes for these dielectrics one by one. Okay, then we have the corona chapter, the high voltage generation. Similarly, we will discuss the high voltage generation for the AC, for the DC, and separately for the impulse. Okay, so we will design the generators for these HVAC, HVDC, and impulse. Then we will discuss the high voltage measurement techniques, the high voltage testing, and the application of high voltage equipment. Okay, so that is all about the high voltage introduction. That is all for the moment. Uh, Thank you.